Hello everybody. Today I want to explain you something related to the presentation which I want to have it for Valencia in Spain for EAS conference. Now let me share my screen. Yeah, it's about Böhm Vitense Gap. First, I want to explain you what is the Böhm Vitense Gap. Erika, Helga, Ralph, Böhm Vitense, simulations, and conclusion and references. First, what is the Böhm Vitense Gap? Böhm Vitense Gap is a discontinuity in the color distribution of A to F type stars along the main sequence. Convective transport both in the interior and in the atmosphere yields a very sharp transition between structures. These produce a sudden change in the T effective of stars around T effective around 6,800 Kelvin. Böhm Vitense in 1970 realized that there could occur a gap in the colors of stars when the atmosphere changes from radiative to convective in deep layers at T effective around 7,500 Kelvin or BV between 0.22 and 0.28 magnitude. There are two possible ways in which convection might alter the color. First, the temperature gradient in deep atmosphere layers becomes smaller than the radiative gradient. And the second is the photospheric granulation associated with convection originates temperature inhomogeneities, which again redden the BV. Rockford and Container re-examined the star distributions along the main sequence of 9 open clusters. In 6 of them, they found evidence for a gap at BV around 0.35 or T effective around 7,000 Kelvin. Even the small current variation from cluster to cluster may be a clue to the gap reality. If it were due to the effect of metallicity on the location of the open clusters, which is expected from the theory. The highest, which seems to have the reddest gap, has metallicity somewhat larger than solar. Here is in the diagram of the highest by Dantona and et al. A short diagram of the highest field squares are single stars, open circles are variable stars. The corresponding color histogram is shown at the bottom. The beam at BV between 0.4 and 0.45 includes 15 stars, and the beam between BV between 0.35 and 0.4, which identifies the gap, includes only 4 stars. MLT dash and dot dashed line and FST thin line. Sorry, here. Thin line, which MLT means mixing length theory, and FST means full spectrum of turbulence. Model isochron for 600 million years are shown, shifted by 0.5 magnitude for clarity. The kink in the FST main sequence is very evident, while the MMT sequence is much smoother. F.D. Antonam and her colleagues used the new Vienna University model atmospheres computed with either MLT or FST as boundary conditions to interior computation adopted the same convection model. They found that the models with FST provides a discontinuity in the mass versus color relation at BV less than 0.4. The MMT models do not show this behavior at all. Simulations of the color distributions show that this feature may indeed produce a gap at BV less than 0.4 and a clustering of stars at BV between 0.4 and 0.5. The stellar structures computed with FST showed a very sharp transition from radiative to convective envelopes. Here you see the highest HR diagram is compared with two simulations from D. Antona et al. You see the highest HR diagram is compared with two simulations containing 100 stars between 1.2 and 1.7 solar mass, randomly extracted from a salpeter mass function distribution following the FSC or MNT model color isochrone of 600 million years. At the bottom, the FSC dashed line MNT color histograms are shown, scale at the right. And the MNT simulation is shifted by 0.7 magnitude, and the FSC won by 1.2 mag for clarity. And the conclusion is the gap location and width depend slightly on metallicity, age of the studied sample, and the evolutionary phases washed out the feature. These are the references, and thank you. Thank you for your attention, and see you next time. Bye.